Okay, welcome to the worksheet mole conversion practice problems all over the map. So in this worksheet we're going to get some good practice with making conversions among all four of the places on the subway map. Alright, so number one, 54 grams of aluminum. Let's see here. So it says calculate the number of atoms. Alright, so let's just go take a peek at the subway map for a second. We're being given a particular number of grams of aluminum. So we're starting here in the mass station. So we've got to do the conversion. We've got to divide by molar mass to convert to the mole. And then from the mole, we need to multiply that number of moles by Avogadro's number to get it over to the number of atoms. Okay, so graphically, that's what we got to do. All right, so number of atoms equals 54.0 grams. Okay, so we got to convert that into moles, and to do that, we multiply by 1 over the mole, and then the atomic mass of aluminum is 27.0 grams. Okay, so when we divide 54 grams, that's the amount that we're given, by the atomic mass, or the molar mass of aluminum, then we're going to be left with that amount in moles. And I think you can see that, 54 divided by 27 is equal to 2 exactly. So we have 2 moles of aluminum. And then, to get this into the number of atoms, we multiply by Avogadro's number times 10 to the 23rd over 1 mole. Okay, and when we plug that through, we get an answer of 1.20 times 10 to the 24th aluminum atoms. Okay, so there we go, 1.20, because we were given 3 significant figures in the mass, and we can keep 3 significant figures in the answer. All right, let's scroll down, number 2. Now this one is very similar, so I'm just going to give you the answer. 2 times 10 to the minus 8th gram of beryllium turns out to be 1.34 times 10 to the 15th beryllium atoms. Okay, and oops, looks like we can only keep 2 significant figures. So technically I can only keep the 1 and the 3 here, because in the problem is giving us a mass that's only to 2 significant figures. Okay, so technically this is our answer. And always be sure, again, don't forget after you calculate a number, that number corresponds to something physical, and so you've got to put the units here, beryllium atoms. All right, let me make sure my time is up here so I can see it. All right, there we go. Moving on to number 3. Okay, this time we're going to go in the opposite direction. So we're being given the number of atoms, and we're being asked to find the mass. So conceptually, we're starting over here with number of represented particles. We need to this time divide by Avogadro's number to get to the mole, and then to turn the mole into mass, we need to multiply by the molar mass. Okay, so back to the problem. So the mass is equal to 6.02 times 10 to the 24th atoms. And as we said, we need to divide that by Avogadro's number, which is 6.02 times 10 to the 23rd over 1 mole. Now, I'm going to use the MOL abbreviation. Now, I think you can see, just, if you look at these numbers, I think you can see that the number of atoms that we're given is 10 times as large as Avogadro's number, exactly 10 times as large. So how many moles do we have? We have 10 moles of tantalum. And then we're going to take that, and to convert this to a mass, we have to multiply 10 moles by the molar mass. And let's see here, tantalum molar mass is 181 grams over 1 mole. And when you, so atoms cancel, whoops, so I should have had atoms down here, and then moles cancel, and we're left with the gram. So over here, the mass of that many atoms of tantalum is 1,810 grams. And I'm trying to be, again, conscientious about the number of significant figures. We were only given 3 significant figures in the problem, so 3 significant figures in the answer. So 1810 grams. All right, moving down, number 4, same approach, and the answer you should get is 79.7 grams of helium. 79.7 grams of helium. All right. Okay, now let's see here. Number 5 again is pretty similar. Just if you want to check, make sure you're using the right molar mass. The molar mass of sodium oxalate is 134.0 grams per mole. So that's 134 grams per mole. That is the molar mass. And then with that, you should be able to calculate the mass of that many formula units of sodium oxalate. Oh, and the answer, as promised, would be 26.7 grams of sodium oxalate. Now again, I didn't say this explicitly, but I hope, the way to make these videos the most effective, to help you the most, is, I want you to work through these problems as best you can yourself and use the video to check yourself. Or if you need a little hint just to get started, you can use it that way. All right, number 6. So these are just a couple of simple problems just to make sure that you know how to get from the mole to volume. And just as a refresher, so the volume is, let's take a look at the mole map real quick. All right, so you're being given a certain number of moles, and we're going up to the volume station. So to get there, you're going to take the number of moles given, multiply by 22.4 liters per mole, because 1 mole of gas at STP conditions occupies 22.4 liters. Okay, so let's go back. So that's 3.20 times 10 to the minus 3 moles, and we multiply that by our conversion factor between moles and liters, and when you do that, you should get 0.0717 liters. Okay. All right, and I think that that should make sense, that you should have expected a very small volume, right? Because you're being given something that's far less than 1 mole. And if you remember, if you have in your mind that 1 mole is equivalent to 22.4 liters, and you're being given like 3,000th of a mole, then you should have roughly 3,000th of this volume, which would be a lot less than a liter. So that all makes, kind of passes the common sense test. Number 7 is you work it in very much the same way, and you should get 128 liters of nitrogen. Okay, moving along. Number 8. Number 8 is very similar to problems number 3 and 4 above. So, this should not be a problem, but I'll give you the answer. First of all, the molar mass of aluminum sulfate is 300. Oops, I didn't mean to put a decimal place there. Molar mass 342.3, and that's grams per mole. And then when you work this out, that many formula units turns out to have a mass of 5,230 grams. And again, again, you're given 3 significant figures in the problem, so you can only keep 3 significant figures here. Okay, now number 9. Number 9 is, I'll give you the answer to that. You should get 7.3 times 10 to the 22nd argon atoms, or atoms of argon, whichever you like. Okay, number 10. Number 10, you're being asked for volume, and to begin with, you're being given a certain number of grams of chlorine gas. So let's go back. Let's just double check the mole map. You're being given a certain, oops, what was that? Yeah, grams. Okay, sorry. You're being told the amount of mass of a gas, and so you have to get from here to the mole station, then from here up to volume. So we need to multiply that by, or divide that by the molar mass of chlorine, which is 71.0 grams over 1 mole, and then multiply that by the molar volume. And that turns out to be 40.38 liters. 40.38 liters. 4 significant figures were given, so you can keep 4 here. All right, so that's number 10. All right, number 11. We're getting into the kind of extra credit territory. Well, this first one is really easy. This isn't bad at all. The molar mass of calcium chloride is 111.1 grams. And so when you convert this number of grams to moles, then you should get, let's see, where'd that go? 0.0720 moles, and that's of calcium chloride. Okay. Water. Okay. Well, how much water are you given? You know the molar mass of water. That's 18.0. If you have 1 kilogram of water, that means you have 1,000 grams. So that's 1,000 grams. And then you divide that by the molar mass of water. And when you crank that through, you'll get 55.6 moles of water. Okay, so that's not too bad. Now, part B, it says, assume that the ionic compound, whoops, my pen got out of control. Assume that the ionic compound calcium chloride separates completely into calcium and chloride ions when it dissolves into water. How many moles of each ion are present in solution? Okay, well, let's look at the process of calcium chloride dissolving. Okay, so first it goes from a solid into solution, and when it does that, it's basically like converting a balanced chemical equation to the complete ionic equation. So you're going to get if you have 1 formula unit of calcium chloride, you're going to get 1 mole of calcium ions, or I'm sorry, let me start over again. If you have 1 formula unit of calcium chloride, then you have 1 ion of calcium, 2 ions of the chloride minus anion. And so if you have this many moles of the compound, you'll have that same number of moles of calcium ion, twice that number of moles of chloride. Okay, and I need to stop here, and I'll pick it up there in part 2 because I'm almost out of time.